Today we are going to learn about understanding cross-validation for robust models. We'll explore how to implement cross-validation techniques to enhance model reliability and generalization to new data.
Welcome to our video on cross-validation, a pivotal concept in machine learning. Cross-validation is a technique used to evaluate the performance of a model and ensure its robustness when applied to unseen data. It helps in assessing how the outcomes of a statistical analysis will generalize to an independent dataset. In this video, we'll cover different types of cross-validation techniques, their importance, and how they are implemented, especially focusing on k-fold cross-validation. We'll also delve into handling data imbalances and avoiding common pitfalls, all through practical Python examples.
Cross-validation is an essential tool for evaluating the predictive performance of a machine learning model. It plays a crucial role in reducing issues like overfitting and underfitting by providing an estimate of how accurately a predictive model will perform in practice. This technique helps in assessing the model's ability to generalize to new data, thereby enhancing its reliability. Essentially, cross-validation involves partitioning the data into subsets, training the model on some subsets while testing it on others. By repeating this process multiple times, you can get a robust estimate of model performance. Cross-validation is foundational in model selection, enabling data scientists to choose the most appropriate model based on performance metrics. There are several cross-validation techniques, each with its unique advantages and use cases. The most common method is k-fold cross-validation, where the dataset is divided into k subsets or folds. The model is trained on k1 folds and tested on the remaining one, cycling through all the folds. Stratified cross-validation is a variation of k-fold, which ensures that each fold has the same proportion of class labels, making it ideal for imbalanced datasets. The leave one out cross-validation is an extreme form of k-fold with k equal to the number of data points, testing on one point at a time. While leave one out can provide more insight, it's computationally expensive. Choosing the right method depends on the dataset size and the problem specifics. Let's dive into the step-by-step process of implementing k-fold cross-validation. First, ensure your Python environment is set up with necessary libraries such as scikit-learn. Begin by loading your dataset and selecting the number of folds, k, typically 5 or 10. Use the fold class from scikit-learn to split the dataset into k-folds. For each fold, segregate the data into training and testing sets, train the model on the training set, and evaluate it on the test set. Calculate performance metrics like accuracy, precision, and recall. Repeat this process for every fold and average the results for a comprehensive performance evaluation. Here is a simple Python example. From sklern.model_selection import fold and kf equals fold n_splits equals 5, followed by iterating over folds for training and testing.
Imbalanced datasets are a common challenge in machine learning where certain classes have significantly more samples than others. This imbalance can bias the model's predictions, leading to poor generalization. Stratified k-fold cross-validation is a powerful technique to tackle this by ensuring that each fold has a representative distribution of class labels. Additionally, techniques like oversampling, undersampling, or using synthetic data generation, for example, smoke, can help balance the dataset. These approaches ensure the model receives a balanced view of the data during training, improving its ability to generalize. It's crucial to apply these techniques judiciously to maintain the integrity of the dataset and enhance model performance.
Implementing cross-validation in Python is straightforward with libraries like scikit-learn. For k-fold cross-validation, use fold, and for stratified k-fold, use stratified fold. Here's a sample code snippet for k-fold. From sklern.model_selection import cross_val_score. Scores equals cross_val_score model, x, y, cd equals 5. This performs a 5-fold cross-validation on your dataset. For stratified k-fold, replace fold with stratified fold. After running the cross-validation, evaluate the model's performance using metrics such as accuracy or F1 score. Visualize the results using tools like matplotlib to get insights into the model's predictive power across different folds. While cross-validation is a powerful tool, it comes with its own set of pitfalls. One major issue is data leakage, where information from the test set inadvertently influences the model during training. To avoid this, ensure a strict separation between training and testing data. Incorrectly splitting folds can also skew results, especially if the data isn't shuffled properly. Overfitting can occur if the model is too complex relative to the dataset, while underfitting happens when the model is too simplistic. Ignoring data imbalance can also lead to biased models. Always ensure your cross-validation process is reproducible by setting random states where applicable. Evaluating model performance is critical to understanding its effectiveness. While accuracy is a common metric, it might not be sufficient, especially for imbalanced datasets. Precision and recall provide deeper insights into the model's ability to correctly identify relevant instances. The F1 score, which is the harmonic mean of precision and recall, offers a balanced measure. For binary classification, ROC curves and AUC values help visualize the trade-offs between true positive rates and false positive rates. Depending on the problem at hand, choose the most relevant metric to guide your model evaluation and iterations.
Selecting the appropriate cross-validation strategy is essential for accurate model evaluation. Factors influencing this choice include dataset size, class distribution, and available computational resources. For large datasets, simple k-fold cross-validation might suffice, while smaller datasets benefit from leave one out or repeated k-fold methods. For imbalanced classes, stratified versions are preferable. Consider the computational cost as well, since more complex methods like leave one out can be resource intensive. Align your strategy with the objectives of your problem to ensure meaningful and actionable insights from your cross-validation results.
As we conclude this video, let's recap the importance of cross-validation in building robust machine learning models. We explored various techniques like k-fold, stratified, and leave one out cross-validation, each with its unique application scenarios. Practical implementation insights were shared, including handling data imbalances and evaluating model performance. By understanding and avoiding common pitfalls, you can leverage cross-validation to ensure your models are both reliable and generalizable. Remember, the key is to align your cross-validation strategy with the specific needs of your dataset and problem objectives. Thank you for watching, and happy modeling!